clear now? Yes, we are replacing the continuous equilibrium in terms of discrete equilibrium. The basic idea in FE is replacing continuum to discrete. Continuum equilibrium need to be satisfied at every location in the range 0 to L for x. Whereas here, the equilibrium is satisfying only at 0 and L for values of x. And that implies when these two ends of the body are in equilibrium, it is assumed that the entire region in between is going to be equilibrium. Moreover, the displacement at these two ends is referred as the primary variable, and displacement anywhere inside is expressed as a function of these two nodal displacements. And to get the unknown displacement, we adopted the elimination approach now. Now let us look at the other approach, which is very popular. And most of the time when we develop code, we'll be using the approach what we are going to discuss now. When we are doing with hand calculations in the classroom problems, elimination approach is advantageous. The reason here is in a 2 by 2, two unknowns, one is eliminated, the other unknown straightforward. If you have three unknowns, the original equations are going to be 3 in number, and the equilibrium equations are expressed as in a linear form 3 by 3 matrix. If one of them is 0, we can eliminate that row and column, we are left with 2 by 2. If it is n by n, if the equilibrium equations are n by n with n nodes in a system, if you have m number of nodes constrained to be 0, so the reduced system size will be n minus m. If n is 10 and m is equal to 3, 10 by 10 we can reduce to 7 by 7, maybe a bit advantageous. If it is 4 by 4 and reduce to 2 by 2, hand calculations we can tackle, so it's convenient. Imagine we have a system of size 1000 by 1000 and we constrain only 10 nodes. By eliminating 10 rows and 10 columns here and there, we reduce that to 990. Will it be a convenient? No. To solve a 1000 by 1000 system or 990 by 990, difference is less, but the process of eliminating the rows and columns and rearranging them is going to be a little involving task. In such cases, we need to introduce a different method. Popularly, it is known as penalty approach. We look into the fundamental principle behind this penalty approach, right? And remember, majority of the boundary conditions, what we come across in contact problems, introducing those conditions into FE models have their roots at this location. First, today we are going to introduce a simple boundary condition u1 equal to 0. That is, we are going to represent a clamped boundary condition. Physically, what do you do to clamp it? Physically, what you do if you are going to clamp it? Say we take two flat plates and put them in between and put some bolt and nuts so that this bar is in position between two rigid plates. Or you can weld it to a rigid wall. Some formula to use it. What is the influence of the boundary or the clamp on the system? So imagine here, this is built into a rigid block. This is built into a rigid block, one below and one bottom, and then we put through holes, or we use welding or some other joining process. That's how we physically clamp it. What is the influence of this support or the structure on the bar? Mathematically, we are converting that as the displacement at this node is constrained to be 0. Is it literally 0? When I apply some force, this also has some stiffness, maybe a rigid. Does it also? Huge amount of stiffness. Still, that may be having a deformation. Maybe when the displacement in the bar is 40 millimeters, This may be in terms of micrometers or nanometers. Whatever may be the stiffness, however rigid it is, when there is a load, that will be some deformation which is insignificant. For all practical purposes, that is insignificant. That means a very, very small. When I say zero, a very small quantity, when I am going to say to a computer, it is my zero. How do you define it zero? What value we can consider to be zero? Zero need not be perfectly absolute zero. Maybe something very less quantity we can discard can be referred as a zero. Here you see, zero displacement means a very small displacement, and rigid means infinite stiffness means a finite very large stiffness. Right? When I say it is zero displacement perfect, this is infinitely rigid, perfectly zero displacement. Huge stiffness for the clamping and insignificant, negligible displacement for the part. Is it logical? One way I can say infinite stiffness and zero displacement. Otherwise, say huge stiffness and negligibly small displacement. And this method operates on this distinction. Right? So here, instead of this clamping, for the understanding purpose, I explain this way. This support, let us say, the influence of this support is to give a huge stiffness, a spring on one side perfectly fixed, and this side it has an insignificant, very, very small displacement, close to zero, but not zero. And here we have a stiffness, huge stiffness, penalty. That in mathematical terminology, when I want something to be constant there, I can put some penalty there. We can put a weight. The other term, penalty. If I put a huge penalty, it can't move. That's a terminology we borrow here. And this stiffness is called penalty stiffness. And the method we are going to refer, the method what we develop from here is referred as penalty method. Earlier we have seen elimination approach. Now we can refer the approach of solving this problem is penalty approach. Try to understand the philosophy, not the approach of introducing that. If you want to tackle something new, some problem new, no one has tackled so far. But if you can understand the problem physically, possibly you can establish a new method to tackle that. Once you understand the philosophy behind this approach. So, we refer this as penalty method or penalty approach for incorporating the boundary conditions. Earlier one is elimination approach. I think I cannot given very clearly. And this is the penalty approach. What we are doing here, we replace the support clamp with a spring of huge stiffness that we refer as penalty stiffness. And the side, the rest of the thing is intact. Now let us look at the potential for this now. Our system is now, we can write half UE transpose KE UE minus UE transpose RP. Without brackets, I am writing a simple form. This is the functional for the problem without the support. The same thing we have taken as this. Only thing I have not put in the brackets to save some time. How can we bring this into the mathematical model? How can we bring that KP into the mathematical model? How can you bring the influence of this penalty or the support into the mathematical model? Directly we are bringing in the boundary condition into the mathematical model. Remember that. Boundary condition, one way we eliminated that, we have used in one form. Now we are going to introduce the boundary condition into the mathematical form in a different route.